Hey everyone, hello. Our group is Smart Campus. The goal of this project is to install some smart technologies into the campus in order to rectify some of the issues we deem present within the current campus as well as increase functionality. So for our group we have 6 team members which we separate into 2 sub-teams, a hardware team and a software team. For the hardware team it consists of myself, Brandon Saez, Dojikovic, and Zachary Vacco. And then for the software team, we have Jonathan EECE410, Tyler Kraft, and Steven Toscano. So, given our experience here, we were able to categorize some of the issues into 3 categories: power consumption, crime, and functionality. Now, regarding power consumption, it's often the case that within a classroom, devices are left on, sometimes overnight, sometimes over the weekend. This is unnecessary power consumption. Regarding crime, regarding the Manhattan College incident report, 3 of the most frequent crimes would be burglary, shark abuse, and alcohol abuse. And then regarding functionality, even in the case now, it's often the problem that the room is either too warm or too cold, and obviously it's quite uncomfortable for everyone right now. And also in other cases, sometimes equipment is broken within the room or it's not operating correctly, which also leads to timing problems. So we aim to rectify this with a smart campus system. We believe implementing smart technologies will reduce energy consumption, enable usage monitoring, reduce some crimes by improving response times, and regarding functionality, we could have controls to obviously regulate temperature in rooms and monitor equipment.
Okay, so as Brandon was saying, our focus of an IoT smart campus, our focus would be to approach it from an energy conservation standpoint. As you can see in this picture, devices have been needlessly left on in a vacant room, many times overnight. So our system aims to mitigate this problem by smartly controlling power consumption.
So to accomplish our goal, we decided to lay out some requirements so that we are sure to fulfill what we propose as this issue. The system needs to have energy monitoring and control so that a user can view energy usage and decide how the system should operate. The system should have automated room control so that devices in a room can be controlled automatically without the need for human interaction. The system should have machine learning so that the system can learn when devices are being used and make intelligent decisions when these devices should be turned on and off. The system should be accurate so that any undesired one-off scenario doesn't skew our data in our database. And the system has to maintain a low cost so that when the system is expanded beyond one room throughout an entire building, the cost does not become overwhelming.
So in order to meet the project requirements that Joe just laid out for us, our system will consist of 3 devices. The first device is a smart outlet, which will give us control over devices that are plugged into any outlet. The next device will be a smart switch, which will give us control over the lights of the room. And then lastly, we will have a smart hub, which will have a proximity sensor and a temperature sensor. The proximity sensor will help our system be notified when the room is occupied or not, and the temperature sensor will start to log data related to the temperature. We'll implement machine learning in 2 aspects, one being pattern recognition. The system should be able to adapt to when the room is occupied or not, and also we'll implement machine learning to monitor the power usage of devices. Here is our current design for the smart outlet that we worked on this semester. We have AC power going to the power supply, outputting 5 volts. In order to power our microcontroller and Wi-Fi module, we require 3.3 volts, so we included a voltage regulator. Attached to the microcontroller is our relay circuit, so we'll be receiving controls from our back-end application to turn devices on or off, which are connected to our outlet. It should be noted that our current design of the power supply and voltage regulator are separate, but as our design matures, we hope that the output for our power supply will be 3.3 volts.
And so the design for the power supply circuit it'll be able to convert 120 volt RMS to 3.3 volts DC. It'll do this through the use of a diode bridge and a high-frequency PWM switch, which will enable us to use a small form factor step-down transformer. This is a key constraint to this circuit because it needs to be able to fit in a standard sized game box or a custom enclosure.
So shown here is the relay circuit for the smart outlet. This is basically going to be controlling the line power to the outlet. It's important to note here that a latching relay is used. Latching relay, unlike a non-latching relay, requires a single pulse to switch states. This was done in the constraint of power consumption. Obviously, if you use a non-latching relay, we'd have to constantly send a signal, which would be wasting unnecessary power.
Okay, so one of the long-term goals of our project is to have it implemented campus-wide. In order to do that, we had to develop a embedded control framework that could that our current and any future smart devices could be built on. In that control framework, we have our microcontroller, which is a low-power variant of the PIC-18 microcontroller family. In addition to that, we have a Wi-Fi module, which connects to JasperNet and ultimately to our back-end database, as well as an SRAM chip, which is a fail-safe for the unlikely scenario that the module disconnects from JasperNet. If that were to happen, the module could continue to take its measurements, storing them in the static RAM until it reconnects to JasperNet and uploads the data back seamlessly without losing data. And we have constructed a custom printed circuit board for this controller. As you can see here, on the left is the CAD output from Altium Designer, and on the right is the actual module.
So as we stated, a big part of our project is going to be based around power consumption and how a lot of power consumption now is unnecessary. So a current sensor is going to be very important looking forward because we're going to have a way to monitor this. So the addition of a current sensor into our system will allow us to gain real-time information, and it'll allow us to monitor the power usage of each outlet. And as of now, we're looking at the Tamura S22P series all-effect current sensor to utilize those current sensing abilities.
Due to the nature of our system, it was necessary to design a database to store information on the various components that will be interacting with our system, such as devices, different events that can occur with our system, such as button presses or Wi-Fi outages, and authorized persons who will be able to edit or view the database.
The firmware for the embedded controller mentioned earlier, basically the brief way that it works, this is an overview. It basically sits in a low power state waiting for one of three events to occur. One of those events could be a button press in the case of a light switch, as well as if Wi-Fi activity is detected, and for example, if the backend sends a command to the system, or if the periodic polling time has been reached for which it's necessary to take another power measurement. Any one of these three events occurring will wake the device up, perform the required action, and then return back to sleep. The idea being we don't want our current measuring hardware to use more power than it's monitoring. So it's as low power as possible.
So this is a diagram of the front-end software application that we will be implementing with our database and with our system. The user will start with a basic login page with username and password fields. Based on the input information from the user, the system will cross-reference with our authorized persons table in the database to determine whether that person is an administrator or a viewer. If the person is an administrator, they'll be given the option to either edit or view. Should they choose to edit, they will be given a series of prompts where they can edit schedules, authorized persons, and the like. If the administrator should choose to view, or if the person is initially considered to be a viewer, they will be given a series of prompts that they can view, such as information on a specific device or usage charts of a specific device.
For risk analysis, we looked at three main risks that we felt were most important, which were safety, security, and reliability. For safety, In order to ensure that our system is safe, we make sure to both simulate and experiment any build that we come up with before we actually physically build it. And we also make sure that we isolate any power components to ensure that anyone using the device is safe from any stray voltages or power. Security, we need to make sure that any data that is collected by our system is encrypted and protected so that we can ensure the integrity of our data. And reliability, in the case, as John mentioned, that JasperNet does go down, we need a system that will be able to store any data that has been collected without it being altered, and it needs to still be able to be accessed by a user or whoever needs access to it.
Throughout this process, we'll be performing 3 different types of tests. As we have already done extensive unit testing on our hardware, in that unit testing, we've already discovered 2 things that need to be changed, namely our approach to power supply and the choice of a latching relay as opposed to a non-latching relay. Later down the line, we'll be performing integration testing of the various hardware and software modules to make sure that they communicate properly and behave properly under different scenarios. And finally, when the whole system is designed, we will perform acceptance testing in which we throw rocks at it, try to make it break, and fix any bugs that we discover in the process.
So here's a quick demonstration of what we have so far for the smart outlet. Will it show? No, it won't. Because it just no, I don't think it shows up there.
Yeah, try to drag. Oh, yes.
There it is. Okay. So basically, these are the current components of the system, and they are integrated together. With a button push, the relay is switched, which turns on the monitor here. And once again, when the button is pressed again, the relay will flip again, turning off the power to the monitor. It's important to note that within this, there is a button currently. There's a button currently. Ignore the thumbnails. There's a button currently, but in the end, we will have communication using our Wi-Fi module, so we could send information autonomously rather than having to do manual button presses. So with this okay. So for our project, we had the two go no-go milestones in mind. We wanted to achieve roughly 40% of the project by this point in time, and we also wanted to prove the efficiency of our system compared to the current system in place. So as can be seen by this layout, we obviously were able to complete all the tasks that we had set to complete for this semester, also getting a head start on some of the tests we plan to complete in the later semester. So shown here is the comparison between the current system and what our system would do theoretically. Now this was a theoretical calculation done over a week time span for RLC 309, the electronics lab. And here are some of the typical devices in the room, the power rating, the rated power usage, and the number of devices in the room. We calculated these results based on a 12-hour workday and 12 hours not used. Obviously, when our system wasn't installed, devices would be left on, and they would either enter low power state or stay in their regular state. With our device, everything would turn off, and obviously this significantly reduced power consumption, leading to a reduction in power by 32%. Now here is the approximate cost of our system per standard room. In a standard room, we approximate that these rooms will require 3 smart outlets, a smart hub, and a smart switch. Now these are the individual costs labeled here, with an installation time approximated at about 1.5 hours, and about that with minimum wage, we expect the system to cost about $244.56 per room.
So since we do want to, in the long run, implement this into a room in Manhattan College campus, we need to make sure that our project will be up to snuff for any New York City Department of Buildings electrical codes. And along with the listed software standards, we also know that just within the last couple months, there have been a couple new laws passed for the NYC Energy Conservation Code, And the ones that affect us that we want to point out are there is a maximum allowable power limit for the interior lighting power, which is based on the room that you can see in this chart. And there's also a new code update for the timer for a sensor. If you're going to have a sensor controlling lighting, you have to also have a manual input, and the sensor itself needs to alert the system when the room has been vacant for up to 30 minutes or more, so that it can shut the lights off in that room.
So for the future plans for this project, over the winter break and into the beginning of the spring semester, we plan to finish the hardware for the project. That includes the sensory hub and the smart switch. And during that same time, we hope to implement the software application. This will enable us in the spring semester to focus heavily on the machine learning aspect of the project, since that is the main concern for the project, and allow for testing time so that the system will operate as expected. Thank you. Any questions?